So using the change of variables that we got last time, we can now write the nth order contribution to the density operator as plus I over h bar to the n. And now we have these integrals, but the integrals, instead of going from t naught to t and then t naught to tau whatever, they go from 0 to infinity. Remember, that was basically why we introduced the Green's function, was to make sure that we could start the time evolution, the field-free time evolution, at the specific time that we want to, and keep them ordered. Okay, so then now we have d. Now we switch from taus to the t sub n's because we are interested in the intervals. All right, so those are all the integrals over the interval, the time differences. And then we have this sequence of Green's functions, right? And they're alternating. So you have the Green function, interaction, Green's function at the time interval before, and so on, down to g of t1, v, and rho, equilibrium or minus infinity, they mean the same thing. Okay, and then times all the field stuff. So just briefly put I'll put the field stuff in here. So you have E, the field at t minus tn, t minus tn minus tn minus 1, all the way down to t minus tn minus tn minus 1 dot 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 minus t1. All right, so all these fields evaluated at the different times. Well, these could move around. We just write these so that's easy to see the pattern. Right, now what we want to do is essentially, there's a clever trick that you can do where you essentially can separate the G's and the V's. It's almost like a kind of a distillation. Separate the G's and the V's. And the way you do this is by remember a Green function is, in this context, is nothing other than a time evolution operator with a cut-on time. So just like we could have a normal time evolution operator, like u t1, u t1 t naught equals the same thing as u t t naught. Right, you can evolve the system from t naught to t1 and then to t, and you can break that up into however many steps you like. This is the first one, this is the second one because it goes from right to left. Well, we can do exactly the same thing with the Green functions because they're going to be time ordered as well. So let's take a piece, let's take a term, let's just make the Green function analog of this. So if I have g t2 times g t1, this is the same thing as g t2 plus t1. Right. Here we shifted the cut-on time to t2, whenever that is, or to t1 here, and then to t2. So we just moved it twice. So because of this property, when they multiply, they add, they just shift the offset. Then what we can do is we can take a term, let's take the last sort of several terms of this. Right, so the last terms of the GV part of the integrand will look something like, well, it'll be exactly V, G, curly G, T2, V, G, T1, V, rho EQ. Okay? Dot, dot, dot. All that stuff before. Okay, so what we're going to do here at this point is we're going to insert 1, which we can do by putting in G T1 G dagger T1. Certainly that's legal, because G is a unitary operator in Liouville space. And when we do this, what do we get? So we still have the V. The V out front is not actually that interesting, but we have the G, G T2. We have the G T1, G dagger T1, V G T1. Oh, it's hard to draw these script G's. I should practice my script G drawing. Okay, so when we look at this, we see something, hopefully that looks a little bit reminiscent of something that we've seen before. Right? This looks like the transformation of this time-independent operator to some time-dependent picture. Right? It looks like the Heisenberg picture of the operator. Why is it not the interaction picture? It's not the interaction picture because we're not using the H0 Hamiltonian. Well, sorry, let me correct myself. All right, I'm going to go back. Voodoo. Okay. So this G, remember what the G is. The G means evolve with the field-free Hamiltonian or the field-free Liouvillean. So when we do this sort of partial transformation of the time-dependent operator to something that's time-dependent, but we only do it with the H0 part of the Hamiltonian, then this is actually the interaction picture representation of V. So we're going to call it V of T1. So whenever you see V with a time-dependent thing in there, remember that we got it from this. So if you like, this, the definition of this is G T, whatever. I can take out the T1. It's any time. Right? All right, so what's the point of doing that? Well, the point of doing that is we see here we replace this chunk of stuff with this V of T, V of T1, of course. And this becomes the thing we just worked out a second ago. It becomes G of T2 plus T1. All right, well, we can follow this through for all of the terms. So when we do that, this thing will become I over H bar n. All right, so all this sort of, this stuff I wish I had a stamp for. And what happens is all the times will go to the left. And we'll have this one single G function. Because you can keep doing this over and over again. So we'll have G, and now it's going to be totally all of them. So Tn plus Tn minus 1 plus Tn minus 2 and so on down to T1. To the G part. Then we have the V's. And remember, for every single time we do this, we're going to get a new V, right? Because now what's going to happen is we're going to have the second V. Well, we have V of 0 here. So we'll just call this first one V of 0, the time-independent one. Then the next one over is going to be V of T1. And there's going to be another V here, right? Which is going to be now advanced by all of these. I have to put them all over here. Right, so I'm going to have, maybe this is not super obvious, so let me just say, what's the next term over? It'll be G. We have to insert 1 again, but we are going to insert 1 with this time point. Right, so it'll be G dagger T2 plus T1 V. We already have the G over here from the one we just did before. T2 plus T1. And then on the other side, we have to put 1 in. So we're putting it 1 in this form. Wow, those G's are horrible. T2 plus T1. This is the 1, the identity. The one after it's going to be G of T3. Right? So now that's going to get G of T3 plus T2 plus T1. This is going to give us V of T2 plus T1. That's why the time intervals add up in the V's. We don't only have one V with all the time intervals. We have a million, well, not a million. We have an infinite number of V's with with all the sums of the different intervals. All right, so on this over here now for the, so times this, we're going to have Tn, so you're going to have all of them, right? Tn, the last one, the Tn is actually here. We're not going to have it. There's always one extra. So this will be Tn minus 1, the one right before Tn, plus Tn minus 2, and so on. Then the next V is going to be Tn minus 2, plus Tn minus 3, and so on, all the way down to V T1, V0, rho EQ. That's not it, of course, because we still have the fields. So times all the fields, right? And then, you, as I said, you can write them in whatever order you want. Just use the same one. So T minus Tn, T minus Tn, minus 1, T, I'm just going to do minus dot 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 T1. Okay, so that is the density operator, or the density vector, if you want to call it that, and think about it in a Liouville space, which is probably correct, to nth order in the perturbation. Obviously, your experiment or your measurement is going to dictate for you which order you're interested in, or perhaps something about the perturbation itself. This thing here, for example, maybe it turns out that the first order matrix element is 0. So then you have to use the second order matrix element. You know, what would be an example of that? If you were trying to connect a state, for example, like, let's say you wanted, for some reason, to connect the states of a particle in a box. Okay, so the selection rules for a particle in a box are such that you need to change the parity. So if you're in the ground state, let's say the lowest state here, the usual dipole allowed transition is to the first excited state. Why? Because the dipole moment operator is proportional to the coordinate x. So V is just going to become x. If I put an x in here and integrate this, I'm only going to have non-zero elements or non-zero matrix elements when these two states have different parity, which means how they reflect with respect to the center. So let's say you wanted to make the transition from the state n equals 1 to n equals 3. And you might say, oh, I can't do that. And I would say, well, that depends on how you try to do it. So if you go from n equals 1 to n equals 3, certainly one amount of x isn't going to do it. Right? That's forbidden. The integral is 0 for the transition dipole moment. But two field interactions can get you there. So if you square a field, if you have two v's, v and v, that's going to look like v squared, and that's going to look like x squared. Well, x squared, you can put in the integral and integrate that. Okay? So what is v squared? If you draw that the way sometimes people do in chemistry, v squared means you have two field interactions that act sort of simultaneously. Well, you don't know that they have to act simultaneously. In fact, they don't really. If you had an infinitely long, if you had a CW laser, you could still do this. But you think of them sort of acting two fields, right? Two fields will allow you to connect a state with the same parity. And this is what we call in chemistry two-photon absorption. Now notice the photon here is not really necessary. We're talking about classical fields, and you can describe this excitation just fine. So the quantum nature of the light is not necessary. It's just the jargon people use to describe this. But what it really means is the field is just acting twice. So instead of having x as your dipole operator, it's x squared. Instead of having just one field, we'll have e squared. And that's why it depends. The density operators change will depend on e squared, which is the intensity. And then what you'll see is that the probability of making the transition will be the square of that. And so it's going to depend on the square of the intensity, which is how we usually think of two-photon absorption as being quadratic in the power of your laser. The power of a laser is just the intensity, is proportional to the intensity, because it's energy divided by time. Okay, so this is a little bit of a sketch about what you can do with these things. You can describe any kind of spectroscopy using the correct term that's up here. Sometimes you know which one it's going to be, and sometimes you have to do a tiny bit of work on these matrix elements to figure out what it's going to be. Okay, so let's get back a little bit to the actual spectroscopy. I'm gonna start the discussion here where everything is right in front of me, and then I'm gonna have to, of course, erase the board. All right, so what is the spectroscopy going to come from? The spectroscopy comes from the fact that we make a polarization in the material. So polarization means kind of like, a displacement of the charges from the equilibrium position. And if that polarization changes as a function of time, then from pre-quantum mechanics stuff, Maxwell's equations, we know that a field will be emitted from that material. All right, so the way to think about it is we have a certain number of field interactions interacting with our material, n of them, producing an nth order polarization. All right, and this is the definition of that. So P, all P, the total P, is going to be the expectation value of the dipole operator. All right, which is the expectation value of dipole operator is like this. Obviously, I don't know that it's always in my notes. So let's just put an n here to remind ourselves that it depends on how many molecules you have. Now, what is the expectation value? The expectation value is trace rho, and now I'll switch to the notation that we've been using in this development, rho times v. Now, rho is the time-dependent rho. Okay, well, we know how to calculate this in Liouville space, right? We know how to calculate expectation values. So this is also equal to n times the scalar product of this Hilbert space operator, Liouville space vector, with rho of t. All right, and the idea here is that we're going to make the nth order polarization by just taking the nth order density operator expression. All right, so the linear polarization will be when n is equal to 1, little n. The second order one, which might correspond to two-photon absorption or some other kind of like stimulated Raman process or second harmonic, the induced polarization for second harmonic generation, we'll have 2, right? Pump probe, 2D IR, 2D whatever, we'll have n equals 3. Cars, scissors, fizzers, whatever. Lots of different methods that have funny names, but are really just the third order response function or polarization. Now, what our job is to do right now is to use this in conjunction with this general formula that we just wrote for any order of these to identify the so-called optical response function. And you'll see actually it takes like 2 lines. I'm looking at it right now in my paper what the line is. It's the one right after this, but it's going to take up like a quarter of the board just to write that one equation down. But I hope it's very clear that the process here, right? Let's just revise. we introduced Liouville space as a repackaging of information that we had in Hilbert space. Density operator becomes a vector. Operators in Hilbert space are vectors in Liouville space. Operators in Liouville space are commutators in Hilbert space with the Hamiltonian. Or commutators with the operator. So then, what else? We found out that every single thing that we knew about Hilbert space as far as time evolution of the density or the state vector, which followed the Liouville equation, also follows the Liouville equation in Liouville space. It looks more like the Schrodinger equation than it does like the Liouville equation because of the fact that the density operator is a vector, not an operator. And then we recognized that we could make a Dyson series when we had a time-dependent Hamiltonian. We invoked all the things that we already knew about this. We made a Hamiltonian that was composed of two parts. They could both be time-dependent if you want, but they have to be two parts. And then we can associate one time evolution operator with one part of the Hamiltonian and another time evolution operator with the other one in the interaction picture. We generated the Dyson series in Liouville space, and we used the trick of expanding the interaction part while keeping the H0 part intact, and that allows us to get a perturbation series. And then that's pretty much it. All we did then is put in a particular form of the interaction, since we're interested in spectroscopy, which was that the interaction Hamiltonian was minus the field times the dipole operator. In our work so far, the field is time dependent, so it's a time domain electric field, and the dipole operator is a constant. And then we simply did a bunch of math. We did it mostly, I would say, we put in some things and did some substitutions. We replaced our usual time evolution operator with the Green function, and that has the effect of converting this sort of notation with two indices or two times to a time difference, and understanding that we have a Heaviside function in there to give us the turn on of when that time evolution operator takes hold. By using that more mathematical or programmatic way of dealing with the time intervals, we could easily make a variable substitution so that we could replace all the integrals that went in these sort of confusing way from like T0 to all these different taus. We could replace them all with 0 to infinities, keeping track of the time ordering not by the integral limits, which is what we had been doing previously, but by using the Green's function. That allows us to write these much more tractable types of integrals with the idea that in the future, as we go along, we'll probably be bold and switch these electric fields to delta functions, and then that'll allow us to read out whatever's left over because we're going to be integrating. As you'll see, what we're going to read out is the response function. So it makes it seem like we will be able to essentially do experiments that directly get at the optical response function. Now in practice, of course, these fields aren't delta functions, but when you look at this, even though it looks ridiculous like this, when it's like a linear or a second order or whatever, it will look a lot less ridiculous. And what you'll see is that it's basically a convolution. So you have the response function convolved with your fields, and that's an easy mathematical thing to do. And people do it all the time experimentally. Usually they do it the other way around. They take the experimental data, they measure something called an instrument response function, which tells you about this, and then they use a simple mathematical procedure called deconvolution to get rid of that effect. If you're a theoretician, you will most certainly calculate your response function as your main task, but if you want to compare with experiments, you would then convolve it with a finite bandwidth or not delta function pulse instrument response function, and you broaden out sort of your features a little bit. Okay, so that's what's coming up, and it's pretty cool. You'll see we're going to go from this very esoteric expressions to things you can actually do and calculate real spectra.